Hi everyone, welcome back to another video, and in this particular lab what we are going to do is to look at how do we create something we called as pulse width modulated waveforms. This is one of the basic building block of power electronics switching, and we will be using this again and again and again for different labs. So this is one of those familiarization experiments on the kit to understand some components of how do we create a PWM waveform. So what we will need for PWM waveform is a comparator, where you can see here the basic building block of this PWM is a comparator, and we will be providing it with a carrier waveform on the inverting terminal and a reference signal on the non-inverting terminal. So there will be lots of ways you can configure the kit, whether you can provide that carrier signal externally, you can have it generated internally, or the reference signal can be again provided internally or externally depending on how you configure it. In this particular experiment, we will be looking at the very basic piece of this experiment, where we will be connecting it to an internally generated carrier waveform, which will be a sawtooth waveform. Now you will be asking, okay, how did we generate the sawtooth? Yes, we'll talk about it, but in the next experiment. Imagine you have a sawtooth waveform and you have a reference signal. How do we create PWM? Okay, so here you can see the kit right now is configured. No, there is not much to configure in this particular lab. We will not be using the breadboard. We are not connecting anything to any external systems or so on. All we are probing is some parts of the blue board. So what we are going to do is, if you probe the sawtooth waveform, if you probe the VREF, the reference signal, and if you look at the output signal, which is the QT, these are the three signals which you will be seeing in your scope. In this case, the purple waveform is the output of this comparator, which is giving the switching signal, which we'll be using later on to switch MOSFETs, whether we configure it in different circuit configurations or so on. And the yellow waveform is the reference signal, which we can change, as you can see here. So if I change this yellow waveform, if I make it up and down, I can change the width of the pulse. All right. So as if we are encoding this information, which is stored in the magnitude of this yellow waveform, to that of the pulse width of this purple waveform. And who is helping me in this process? The carrier waveform, which is the sawtooth. And there is a simple math you can do to figure out how does the intersection point of the yellow waveform with that of the blue waveform give rise to specific value of the width of the purple waveform. Now in power electronics, the turn on time or the on time of this pulse width divided by the total time period, we call it as the duty ratio, which you might have heard in different contexts. So we are converting basically this yellow waveform into a duty ratio, or in other words, we are mapping the yellow signal to the duty ratio of the converter. And since we are encoding this information, this encoding process has to be linear, right? If you introduce non-linearity here, imagine I'm trying to control this, imagine I'm trying to close loops. If you introduce non-linearity here, that is going to bite us later on, right? The controller becomes more complex and so on. So this encoding process has to be as linear as possible. And if there are non-linearities, we have to put bounds around it such that those non-linearities doesn't harm us when we are trying to put this into a bigger context. Okay, so let me see if I can explain a little bit more. Okay, so here we are playing with the duty ratio. So as the yellow waveform goes up, my duty ratio goes up, and as my yellow waveform, I tune it and it goes down. Okay, but it also we may need to change the switching frequency of our converter, how often we turn on and turn off our devices, right? So in this case, that can be controlled by the time period of the blue waveform. Okay, so the sawtooth waveform, we can change the frequency of the sawtooth waveform, and that will change the time period. Okay, So now what you will be doing in this lab particularly, try to explore how linear is this process as you go through different frequencies and different range of duty ratio. When you are at a very low frequency, which is the lowest frequency here we can achieve is close to around 6 or 7 kilohertz. This looks pretty straightforward, pretty easy, right? It's like, okay, I have a ramp and I'm comparing it and I'm getting the sawtooth waveform. I'm getting the PWM waveform, right? But things become more interesting and more trickier is as we start pushing the frequency higher. We obviously don't run our converter these days at 6 kilohertz. So imagine I want to go to 100 kilohertz. So I need to change my frequency in this case to 100 kilohertz. So let's see if I can zoom in. So roughly we are talking about 100 kilohertz. So now here we are at 100 kilohertz switching frequency. Okay, roughly speaking. So now what happens, how cleanly we have generated the blue waveform becomes important, because obviously what we are doing here is that the ramp is going up and then there is a fall. And when there is a fall in this particular ramp, when you are looking at a large time scale, it's fine, but there are finite time during which it's not exactly a sawtooth, but it has some kind of a falling of age, right? So you have to be careful about when these things become trickier. So if I am trying to push my switching frequency even higher, I need to be careful about what is this discharge time is, and I need to pick up my components such that this becomes a minuscule part overall compared to my overall time period. Another things you can see at the starting of this ramp, there are some non-linearities, and that is coming because of the non-linearities of the how we have generated the sawtooth waveform. So we will study that in the next lab, what caused those non-linearities and so on. But in this particular context, you can clearly see that, okay, we can generate 100 kilohertz switching frequency. And if those non-linearities bother us, what we have to be careful is we have to make sure that once we have fixed our frequency, the duty ratio may need to be bounded so that I can operate my duty ratio or my input voltage, the yellow waveform, within a certain bound. If it goes above certain bound, I lose my linearity in my encoding process. Okay. So good luck with this experiment. What you will be doing in this lab basically is to look at how linear is the process and when does the nonlinearity come into play, how does it impact the PWM generation process, and eventually you will be seeing if there is any bound we have to be doing at particular frequencies. Good luck with this experiment, and I will see you in another one.